There we go, start. Okay, so it is streaming. All right, so I'm hoping that you guys still remember what we talked about last Wednesday about subroutines. Because I just went back to the video to double check, so that I remember what we were talking about. So this is something that you can do as well. Is right before the class, just go to YouTube and retrieve the last email that we have. So we'll go to. So this is a place where you do not have access to because this is all inside. As far as you guys are concerned, you can go to youtube.com/someprofs and then click on videos, and you will get to the list of videos that I have put onto YouTube. And they're all in a reversed chronological order, which makes it easier to find the most recent videos. So in this case, it's 1 week ago, which is the 13th of November, and it's cisp310. So this is the last thing that we talked about in this class. So there's no need, if you're just reviewing, just try to reconnect with the topics that we have talked about so far. There's no need to watch the entire thing. One thing you can do is just to go all the way close to the end, so that gives you an idea of what we talked about in the previous class. So I'm just going to go with this and start with this, and then we'll go ahead and complete this program. So with this program, you can see how we decrement the stack pointer to allocate space on the stack. Okay, if you remember, how we push items on the stack, the first thing we do is to decrement the stack pointer, and then we store to where the stack pointer points to. And that's exactly what we're doing here, because register D is designated by convention as our stack pointer. So we decrement, we store to where that place. But we also mentioned why this won't work. Do you guys still remember? Okay, because you cannot use a label as the second operand of the store instruction. That is not a syntax issue. It has to do with the architecture itself, because the only thing we can store into memory, the only thing that we can connect to the data bus that can drive the data bus is a register. There's nothing else that can drive the data bus. So as a result, there's no way to specify just a label here. The assembler would be kind and tell you that it cannot be done. But that's just the assembler trying to do you a favor to let you know that no, the architecture cannot support this, okay? So we'll start from here and then continue to write the program. So the way I'm going to do this is to use a notepad instead of handwriting it, because I can use notepad and then copy and paste it into the assembler, and then we can actually just run the program. So we'll start up mousepad, and I'll put it right next to this screenshot of the video so that we can just kind of copy a little bit of this, okay? So we have decrement D, which is fine, and then we have std. So instead of putting the label here, the only thing we can do is to use another register. So we have to use register A. But register A is not initialized, so that means you have to load something into register A first. In this case, we'll use your second call to F.
It says
Of F. Okay, fine. We'll be consistent and use second call of F. Okay, so now we can have a JMPI to F, and this is where the label definition is second call of F. Okay. So this entire sequence, okay, and including the label definition, this entire sequence is how we invoke or call a subroutine in assembly. We have to first, allocate a space on the stack to save one space and go like, okay, we're gonna use this new location. Well, I shouldn't say new location, but newly allocated location to store the return address. What return address are we talking about? Well, the return address is the address of the instruction right after the JMPI instruction. So when the subroutine is done, we know where to go back to. Okay, so in this case, the return address is simply known as the symbolic name of second call of F. So we store that into where the stack pointer points to. So this way, the subroutine can also go to the stack and retrieve the return address. Are we doing okay so far with all this? Okay. All right. So now that we are done with the first call, we have another call to F, in the original program, which is right here. So it's going to be about the same thing. Once again, we decrement D, LDI, A with end of main, okay, this time, STD, A, JMPI to F again, and then now we have end of main being here, and we just need a halt instruction right after that. So this is kind of the main part of the main subroutine. There are a few things that we really should do, okay, to complete this program, to complete main. There are two more things we need to do. One is kind of, both are unnecessary, but one is necessary if you want to run this in the when you want to run the program using the command line option, so you can use the trace analyzer. So if you plan to use the trace analyzer, you need to start with a no op instruction, so that when you have to have it here. The other one, the next one, is not absolutely necessary, but it's a good idea to have it. It has to do with resetting the stack pointer. So you can do a LDI D with 0, okay, to 0 the stack pointer. So we are not really loading, even though it looks like we are loading the smallest value into the stack pointer, the intention is loading the address of the byte that is after the highest location in RAM. The highest location in RAM in hexadecimal FF, but if you add 1 to FF, it becomes 100. But 100 requires more than 8 bits to represent, but the register is only 8 bit wide. So 100 is stored as 0. Is that okay? Does everybody understand why we initialize the stack pointer with 0? Which seems to be kind of counterintuitive, because why would we want to initialize the stack pointer with the lowest address in the entire memory space? Well, the answer is, well, that is also known as the highest location. And the first thing we do is we decrement D. So that means when we do utilize D as a pointer, it is actually pointing to the highest location in RAM. So that all works out. So now the next question is, what do we do in F? In other words, F as a subroutine doesn't do a single thing, so it has to return. But how do we return to the caller? You might think, well, since register A still has the return address, we can just do a JMP-A. Well, that is kind of true, but then you have to remember to put the return address into a particular register. There's a reason why we use the stack. The stack is visible throughout the entire program. So we don't want to rely on the registers. So now we want to retrieve the return address from the stack. So I'm going to just write it down here. Retrieve return address from the stack. So this is equivalent to what we call a pop operation as far as stack operations are concerned. So if you remember, okay, a pop operation starts with retrieving an item from where the stack pointer points to, and then we increment the stack pointer. Okay, so that's exactly what we're going to do. So we'll use an LD to retrieve something. Now, which register you decide to retrieve it into doesn't really matter. As long as it is not register D, it's okay. Okay, so you can use register A, B, or C in this case. Because F has a void return type, so that means we don't have a return value. When you have no return value, A is not special, B and C are certainly not special to begin with. So you can use any one of the 3 registers in this case. Don't forget to increment D, because it is the responsibility of the subroutine to deallocate the return address, not the caller's responsibility. So this is an agreement, okay? All of these are about agreements between the caller and the callee, the subroutine being called. Now you might ask, well, why can't we rely on the caller to deallocate that 1 byte that we have used as a return address? That's a good question, okay? It is not a bad question. The reason why this is the convention has to do with, on most architectures, there is a return instruction that does this automatically. So, and the return instruction is always in the callee, or the subroutine being called. So I'm only following that particular convention. Is that okay? Because I don't want to change the convention, so that what you learn in this class cannot be reused in your other classes. So by convention, the subroutine deallocates the return address. Yes.
So the convention is there, but is there any? There's no physical limitation stopping you from having the caller deallocate.
That is correct. So the question is, since this is only a convention, there's no actual physical limitation as far as the architecture is concerned that we cannot shift the responsibility to the caller. So you're absolutely right about that. Okay, but since in a class like this, we have to be you and I have to code in a consistent way, and I choose to use the convention that is consistent with other architectures. So that's why we're still asking the subroutine to deallocate the return address. So let me finish this first, and then we'll kind of get back to what we talk about here. Okay, then we have a JMPC instruction, and it is correct. Okay, this JMP does not have an I because it is not immediate. Where it goes back to is not based on a label or a predetermined constant that is on the right hand side of the JMP instruction. It is based on the value of register C at the time when the JMP instruction happens. So it's dynamic. Okay, is that making any sense? So where it goes back to really has to do with what did we retrieve from the stack earlier. Whatever we retrieve earlier from the stack is where we are going. Are we good so far? Okay. So this is it. Okay, this is the entire sample program where main calls f twice. F is a void function, does not return anything. All it does is to return to the caller. And this is the entire program. So what we can do now, there's one more thing. In some of the CISC architectures, these three instructions are combined into a single instruction, typically called return. Okay, and it's usually abbreviated as RET, for return. But since the TTP is a more or less a RISC architecture, so I go like, well, I can do the same thing with three individual instructions. So I'm just going to do it with three individual instructions, and there's no single instruction called RET with the TTP ASM. Is that okay? Yep, go ahead. The caller is the code that is invoking a subroutine, calling the subroutine, and then the called subroutine or the callee is the subroutine that's being called in the invocation, in the call situation. So the caller is the one doing the action, and then the callee is the one that is being called. The caller is the subject, and the action is call, and then the callee is the object. So are we doing okay with this, with the code, just the way it looks? Are there any questions about any line of this particular sample program? Let me turn on a line number so you guys can refer to the number of a particular line if you do have any questions. No questions? Okay, well, if there are no questions, we'll go ahead and run it. So I copy all, and then we need to go to the assembler. Okay. I really should have bookmarks, for all the pages that I access frequently, but I got around to do it. Okay, we can go to processor. It's kind of, in a way, it's good to show you all this stuff too, so that you actually remember how to do it too. It's my excuse of not making a bookmark for these things. All right. So we get to the source tab here, and you can always erase what is already here, just using the delete key, but don't use any other way to remove content. And then go to the first cell, Control V, paste everything in, and then we go to RAM file to download the code, to download the opcodes. So we go to download as either CSV or TSV would work. And we'll call this call return.csv. Now we need to go to the command line. And I don't think I have any bigger command line here. I can make this bigger if I need to. Okay. And we can go to the temp folder. I think this one starts up the full GUI, which is not what I want, but I can use this. And then we specify dash tty table.
We can't see what you're typing.
Hmm?
We can't see what you're typing.
Oh, you cannot? Okay, right. I can move this up a little bit. There we go. So dash tty table, tells Logisim that we do not want to start with the GUI version. We want to use the command line version, and the output should look like a table. And then we have to supply one more thing, which is a dash load, and that has to do with the name of the file, the RAM file, which is called callreturn.csv. Now we can redirect the output of this program to a file called, I just call it log.tsv most of the time, so the log file has a stable, constant name. But you don't have to do it this way. You can definitely rename the files any way you want. So now the program is done. When the program is done, we can use any type of text editor, including Notepad, to look at the content of the log file. If you're very careful and you go through the columns very carefully, you can actually make out the content of the log file, but it's really difficult to do it manually because everything is in binary and it's just harder, very difficult to interpret. So that's why I made a trace analyzer spreadsheet. So the trace analyzer spreadsheet is going to do most of the heavy lifting when it comes to analyzing the log file. So this way you don't have to spend your time to basically parse the output of the log file. So we can go here and then we go import and then we upload. If you already have those files uploaded, you can select one of the other tabs, but I don't. So we want to go to log.tsv. And then we specify that we want to replace current sheet, okay, just one single sheet of the entire document. The separator is tab and tab only, and then we do not want any conversion, okay. Make sure you select no, as the last option. Then we click import data. Takes a while for this to run. You can look at the progress bar. When it's done, that bar will go away. So this might run a little bit slow on a slower laptop computer. If you have a Chromebook, it might actually struggle a little bit. Might take like 30 seconds to run. Okay, this computer is relatively fast, so it's not too bad. So okay, now that it has run, we have a clean output. So the third tab is what you need to refer to. Sheet 1 is the raw data that we import directly from the log file. Sheet 2 has some kind of magical stuff that is doing some of the analysis. The analysis tab is what you need because it just summarizes stuff in a very clean way. So we'll look at the output. You can see some rows are empty. Just ignore those particular rows if they're empty. The first column is your PC, is your program counter. It tells you which instruction am I executing based on its address. And everything is in hexadecimal. There's nothing in decimal in this spreadsheet. So location 00 has a no-op instruction, and a no-op instruction doesn't do a single thing. So we can see that no RAM is being read, no RAM location is being written to, no register got changed, and none of the flags in the flags register got changed. Okay, but that's no-op, okay? Location 01. Location 01 is the one that initializes the stack pointer, which is register D. So it does read the two locations, 00 this is the constant that we put into register D, but you will see that register D did not seem to change because all registers start with a value of 0 to begin with, and the log file would only put an entry in when there is a change. So if you're loading a 0 into a register that is already 0, it doesn't cause it doesn't make an entry out of that. So you just have to make an assumption that if you don't see anything, it has the previous value, and all registers and all RAM locations other than the program start with 0 by default. Then what about 03? It's reading 03. What is it doing here? This is the fetch operation. Okay, so it's fetching the opcode at location 03, which turns out to be EF. So when we execute the opcode at location 03, the result of that is D, register D is now FF. So can anyone guess what is the opcode EF corresponding to? Close. Decrement, yes. Because register D just got decremented to FF. Okay, very good. But how do we know this is not subtract? Okay, how do we know that not because of one of the registers is 1 and we are subtracting 1 from register D? How do we know?
Well, I mean, we didn't load anything into any other register.
That's true, and there's one more thing. The next opcode is at location 04, and well, okay, I shouldn't say that. But we also see that none of the flags got changed, okay, which can happen, if the subtraction instruction is not changing any one of the existing flags, it won't reflect any flag changes either. All right, so that's the decrement. And then 04, let me scroll down a little bit, and then we'll take a look at what happens at location 04. So at location 04, I'm going to even highlight, the stuff that we should be looking at. Yep.
Sorry, before we move on, if all of the registers are initialized with 0, why did we have to load in 0 to
To emphasize that, when your program starts, the stack pointer should be initialized, because we're working with an architecture, where the beginning of the program has the register initialized to quote unquote the right value, assuming we want the stack to be at the highest possible location. But if that is not the case, then you have to initialize it to where you want the stack to begin. In the C and C++ program, you don't have to do that, because by the time you get control in main, the stack pointer is already initialized. But that is only the case when you have a single threaded C program. Some of you will probably get into multi-threaded programs in C or C++. So in those cases, for every thread that you start, you have to allocate the stack for that particular thread. So there are concepts about threads and processes. A process can contain multiple threads. It has to have at least one thread, but it can have more than one thread. The main thread starts with a stack that is pre-initialized for you, so you don't have to do a single thing. But if you want to start additional threads within the process, then it is up to you to allocate the space for the additional stacks. But every thread needs its own stack. Okay? So is that okay? How many people have heard of multi-threading programming? Okay. So that's the kind of stuff that you might need to think about, if you want to get into multi-threaded programming in C or C++. If you do multi-threaded programming in other languages, the stack management is usually pretty much done for you, so you don't have to do that. All right, so getting to location 4. Okay, so when you get to location 4, we look at location red. Okay, so 09 is red. Location 05 is red. It has a content of 09. And that 09 is in return put into register A. What is the significance of 09? And what instruction are we talking about in the original program? Which instruction puts something into register A? Yep.
Loading the memory address of the label?
Yes. So we are loading the return address into register A. Okay, that's the LDI instruction. And you can see this is an LDI instruction because it takes up 2 bytes instead of 1. Okay, so that's the other clue. At location 06, this is the only change. Okay, so you look up the column, it says your RAM is written to. We wrote something into location FF, and the content we wrote into that location is 09. So which instruction did this? It's go ahead. The ST, yep, the store instruction. The other Yeah, the store instruction stores whatever A has, which is 09, to wherever D is pointing to, which is FF. So the end result is the location FF in RAM is now overwritten with 09. Okay, so if you look at the notation carefully between column B and column C, they're different. Column B uses equal equal because all it wants to say is, oh, I found 09 to be at location 05. I found F3 to be at location 06. So that's why it is using double equal, because all it's trying to tell you is, oh, I now know that this location has this content. That's all column B is trying to say. Column C, on the other hand, has a single equal, which is the assignment operator. We are changing location FF to have the content of 09. So that's why, so there are minor differences, but they are significant. Okay. So we are now just setting up everything, and then we get to location 07. Location 07 is a jump instruction. It corresponds to the JMPI to F instruction. So that's why after 07, we continue execution at 10. Okay. Normally, we do not do that, because normally, okay, the longest instruction we have only takes up 2 bytes, right? So after location 07, even if location 07 has an opcode, like in this case, that has 2 bytes, the next location should be 09 and should not be 10. So if it's off by more than 2 bytes, we know it is probably some kind of a jump instruction. And in this case, it's a JMPI to label F. So we end up at label F, which is 10 in hexadecimal. Okay. So when we get to the subroutine F, okay, which is starting at location 10, the first thing it did was to put 09 into register C. So now the question is, where did it get 09 from? It's coming from the memory location of FF, which is what the stack pointer is pointing to. So this is the result of the LD instruction. We are loading whatever the stack pointer is pointing to. Okay, the stack pointer points to location FF. So we are loading the content at location FF, which is 09, into register C in this case. So we are retrieving the return address in this case. So after we retrieve the instruction, the next thing we do is we somehow change the stack pointer back to location 00. So which opcode did that? Increment D. Okay, so we increment D to deallocate the byte that was used earlier to store the return address. And then at location 12, yes? For location 10, that's a good question. That is a good question.
Like, is that just part of the trace analyzer?
It's part of the side effect of the trace analyzer. It's definitely reading from location FF, and the content at location FF is 09, and it put it into register C, but I cannot tell you why it got updated twice. That is not normal, because I only look for changes of the registers. So that's interesting. I can look into it later. Yeah. And then at location 12, or location 12, because it's in hexadecimal, this is the JMPC instruction. In other words, we are basically just copying whatever register C has, which is a 09, to the program counter. And that's why the next location we execute is at location 09, because the program counter points to the RAM location where we should fetch the next opcode. By changing the program counter, we change the flow of the program directly. Is that okay? So when we get to location 09, it decrements the stack pointer again. So we're basically repeating the same thing, except this time the return address that we are saving is 0F instead of 09. That's the only difference. And it goes through the same motion again, but you can see how in the subroutine, it now also knows that it's supposed to use 0F as the return address, so that execution continues with 0F over here. But because 0f has the halt instruction, so that's why there's nothing after this, because the halt instruction 1 doesn't do a single thing, and 2, it doesn't move on. And the halt instruction, when we execute the halt instruction, it also sets the halt output pin in the processor, and that is that's what's telling the command line version of Logisim to stop logging. So that's why we have all those kind of interesting output pins, both for logging, so that we can analyze, the stuff and get all these conclusions, but also to tell the command line version of Logisim when to stop. So there's a little bit of, kind of cool features, built into Logisim at work here. So is that okay? Does everybody kind of follow, how the flow of the program changes, and as well as how the stack is being utilized? So we good? Right? Cool. So if this is good, then we're going to go back to the program. And I think I can just make some minor changes to the source code here. So instead of changing the code in Notepad, I'm changing it direct to the source here. So the use of label is good in the sense that it is very clear what we are loading into register A on line 4. The label is defined here. We are using that as the return address. But it is not good in the sense that copy and pasting code for the calling part is not going to work very well, because you have to change the return label for every single time you copy and paste this code. So from that perspective, it's kind of like, I wish we don't have to use a label. So as it turns out, there is a way to avoid the use of a label. So in the postfix notation, a dot has a special meaning, a single dot. So a single dot is basically saying, oh, the dot is representing the address of the instruction that we are writing right now. So in this case, the dot would be the address of the first byte of the LDI instruction. I have to say the first byte because LDI needs 2 bytes. Okay, so the dot is referring to the address of the first byte of the LDI instruction. Are we good so far? With this, we can now say, oh, but now we can use a relative distance from here to or we need to switch to, because we can now count on line 4 we have offset 0, 1. On line 5 we have offset 2. On line 6 we have offset 3 and 4. And then so when we get to the address of the decrement, it should be at an offset of 5 bytes from the first byte of the LDI instruction. So now we can say dot 5 plus. Now it's not dot plus 5 because it's postfix notation, so you have to supply the numbers that the operator is supposed to work on before the operator itself. So it's in postfix notation, but this would do exactly the same thing as putting, referring to the label over there. Okay. The best part about this approach is it works as long as the ordering of these code is identical. You can now do the same thing, over here as well. So instead of using end of main, we can now say dot 5 plus, and it will work the same way. Now, obviously, what if I make a mistake, right? I want to double check and make sure that I don't make a mistake first. When you go to the Assemble tab, it will tell you whether it works or not. I don't even have to run the program to check it. So we can look at line 4, and it says it's loading a 09 into register A. That's consistent with the previous program. It is also consistent with the label definition of second call of F, because when you track down this row here, the location of second call to F of F is also location 9. So we know the way we did the calculation using the dot notation is in fact correct. And we can do another check, with the other LDI instruction, which is on line 9 right here. So if you track this down, it's loading 0F into register A this time. Now, is 0F the correct, constant? Is that really the label? Well, let's look up the label definition. End of main label definition is here, And if you go all the way across, it is 15 in decimal. 15 in decimal is in fact F in hexadecimal. So the calculation is in fact correct. So this is how I can double check and make sure that dot 5 plus is the correct way to calculate the return address without the use of any label. Is that okay? Yep. Mm-hmm.
Why would you want to do that instead of using a label?
Because if you use labels, then you are exposing your program to typo mistakes. And if you copy and paste without modifying, then you will be branching to the wrong place when the subroutine returns. So those bugs are really kind of nasty to debug because, yeah, so they're just kind of nasty bugs to begin with. So now we don't need this label, we don't need that label. Every time we call, we can just copy and paste this portion. This label has to change depending on which subroutine you're calling, but at least we don't have to use have to use additional labels for every single place that we can return to. Mm-hmm. So is that okay? Does everybody understand the basic mechanism of invoking a subroutine and also how to return from a subroutine? Are we good? Okay. So the stack is really useful in this particular way. The next topic we're going to go over is how do we return a value, okay? In other words, okay, so I'm going to erase all this stuff here. So I'll give you a different subroutine, okay? So this subroutine has a name of 5, and guess what? The only thing it does is to return the constant of 5, okay? Not a very exciting kind of subroutine. So now the question is, how is it implemented? In other words, how do we tell the caller, okay, that the return value of a subroutine is 5, okay? So 5, has a type of integer. Anything that has a type that is what we call a scalar, okay, would use this mechanism. A scalar, S-C-A-L-A-R, okay, basically refers to all the integer types, signed or unsigned, double, float, those are all called scalar types. Okay, char is a scalar type because char really is signed 8-bit integer, so it's definitely a scalar type. So all of those are called scalar types. Every time you have a subroutine that returns a scalar type, the convention of most compilers is it would use a register to store the return value. And the convention is it would use register A to store the return value, or register 00, to store the return value. Once again, it is arbitrary, okay? Can't we use register 3 or register 2, or register C in this case instead of register A? Absolutely, okay? So it really is just another convention of most compilers. So that means this particular subroutine is very easy to translate. All it translates to is 5, which is the label corresponding to the entry point of the subroutine. Then we use a LDI A5 to specify the return value is 5. That's all, okay? The caller, because of the agreement between the caller and the callee, they both understand that, when the caller gets control, it would go to register A to say, okay, callee, what is the result of your calculation? I'm assuming it is in register A. That's the whole deal, okay? So now we just have the usual return sequence of instructions, which start with the LD. I cannot use register A anymore, but B and C are both available, so I can use register B this time. Increment D is still needed because I still need to deallocate the return address from the callee's perspective. And then a JMP B in this case, because I'm using register B as the temporary register to store the return value. So are we doing okay so far with the concept of returning a value? Yes, go ahead.
Well, I was just wondering, can you explain what line 9 is? What line is 9?
Line 9 is retrieving the return address. It is part of the agreement between the caller and the callee that at the entry point of a subroutine, the return address is stored where the stack point is pointing to. That's the deal. It all has to do with the agreement between the caller and the callee. Yep.
So you said this is how they would store or return any scalar value, but what if it's wider than 8 bits?
So with this architecture, you cannot you cannot do anything other than an 8-bit thing. With a 64-bit architecture, the widest thing you can return is a 64-bit thing, which includes just about everything that you need in a modern program. Because I think there are no, GCC at least does not have a type, integer type, that is wider than 64-bit, that's also a scalar. So that's okay. In the case of a 32-bit architecture and you try to return a double, it would either use one of the floating point registers or it would put the 64-bit number into two 32-bit registers. And once again, that's an agreement between the caller and the callee, of, okay, if the caller is expecting a 64-bit thing, but each register is only 32-bit wide, then it is an agreement, that, okay, we'll first use register EAX and then we'll use register EDX for the most significant bits. So it's just an agreement between the caller and the callee. But that's a very interesting question because the larger scalars is not that much of a problem because the largest of all the scalars has 64 bits, which is still a fixed number of bytes, right? Okay. But what about structures? What do you do when your subroutine is returning an entire structure by value? So you're not even returning the address of a structure. All addresses are, by the way, scalars. Okay, so if you return the address of something, it's considered scalar, put it into a register. So what if you're returning a structure? A structure can be really small, can be actually non-existently small, but it can also be really huge. So when it comes to returning a structure, it is actually returned through the stack. Okay, it's complex. Okay, so we are not going to get into that just because of the complexity, and we don't have a lot of space in the toy processor, so we don't really have a lot of space to play with returning an entire structure. It's also awfully inefficient. So even though it is a possibility, even though it can be done, unless it really makes sense, it makes your program a whole lot easier to read, or it is also required, don't try to return the structure because it's a very, very inefficient way of doing things.
Even in 430, we would always just return an address.
You can return an address to a structure, but I'm just telling you could do this. So let's say you have a structure. This is all just regular C, not even C++. So if you have a regular structure called X here, you can have inside the structure an array, right? Okay. So you can have an array of 256 bytes for the string. You can have another array for the doubles. Okay. You can say values, and it is like 40. There are 40 of these things. So in a particular function, you can actually declare this in C and C++. You can say struct X, F something, okay? And you can return an entire structure this way. But there's no easy way to specify what you're returning other than this, okay? So you need to have a local variable V like this, and then you do a whole bunch of stuff with V, okay? Okay, initialize V, okay? Then you can return the entire V. So as a result, you're basically, there are two, you're reserving twice the space of a regular struct X on the stack to do this. One has a name called V that is inside your subroutine that you have access to because you can say V dot blah, blah, blah and do stuff with string and values. But when it's time to return, what's going to happen is the compiler will generate the code to copy your local variable V to another chunk of space that you have no name to access to, but the compiler would give you that space and say, okay, use this space as the return value. So you basically end up with a memcopy function to copy the entire structure from here to the unnamed space that the caller has access to. So it's extremely inefficient. It's just a bad way to do things. And stack space is kind of, I wouldn't say sacred, but it is, it's limited. So we really should not be using stack space unnecessarily like this. So even though it can be done, it is typically not necessary nor a good idea to pass an entire structure or return an entire structure like that. So I'm going to erase this because it's just not a very good idea. All right, so now we're going to move on to the next concept, which is, let me see, what is the name of that? I have one of the two concepts to talk about, but I have to remember the sequence of the modules and also your lab for today. There's a new lab for today. So the lab for today is called Parameters and Local Variables. Okay, so, nope, that's not it. That's the topic. The lab for today is Parameters and Return Value. There we go. So this is our lab for today. You do have 1 week to work on it, but I would like people to at least get started today. So we need to talk about parameters next. Okay. In other words, okay, so this is 5, okay, not very exciting. I'm going to erase this. So I'm going to say, what if I have something that's slightly more, interesting, okay? We'll call it sum. We have x, we have y, and it is going to do something quite exciting, which is returning x plus y. Okay. So, as you can probably tell, this program is not very useful because all it does is to illustrate the concept. I'm going to make a little bit of change here, okay, I'll call it diff, and we'll use subtraction instead. The reason I make this change is because, with addition, you can kind of do it either way, right? The ordering does not matter. It is commutative, but subtraction is not. So this will emphasize, the ordering of the parameters. Okay. So how do we do this? The first question is, where do we put the arguments corresponding to x and y? In other words, if I have a main program corresponding to illustrate this point, and all I do in the main program is say diff of 17 and 56, okay? This is my entire program. And of course, some of you will say, but that's stupid. This program doesn't do a single thing. It doesn't even store the return value of diff. You're absolutely correct. Okay, C does not require you to do anything about the return value of a subroutine call. You can toss it away. How many people utilize the return value of C in or C out using the less than or the greater than operators? You toss it away, right? Most people just toss it away. The last one, by the way, you toss it away because it returns C in and C out itself, so the whole thing can be chained. Okay, there are many other C functions that actually return the value, like string copy. String copy actually does return the value. Does anyone know that? No? Well, that's because we ignore that result, okay? You don't have to use the return value. So anyway, I'm just going to do this because I have not talked about how to use a local variable yet. So we are only focusing on this call. What will this program look like in assembly? That's our focus right now. Are we good so far? Okay. All right. So what we'll do is we are going to take a look at this program on the left-hand side, and then we'll go ahead and write the assembly code on the other side, right here, okay? So the main program, okay, this is absolutely not needed because, this is the first part of the program. It always starts with location 0, okay? So we start with a no op just to make the command line version of Logisim happy. LDID with 0 to emphasize that we are initializing the stack pointer, also not necessary, okay? So now we move on to the actual part that we need. How do we pass 56 and 17 as arguments to the subroutine? So the actual logic is actually quite simple. We want to push the last parameter first, and then we push the first parameter last. So we push 56 on the stack first, and then we push 17 on the stack. Then we do the usual thing of calling the subroutine. Okay, so call diff. And then we also have to clean up the arguments because they're pushed on the stack. And that's it. Okay, this is basically what we need to do. So now we're going to go back and say, but how do we do this? So before we move on to talk about how this is done, do we have any questions about what it means when we say push 56, push 17 on the stack? Do we understand what that means in the context of stack operations? Are we good? Okay. So we'll go ahead and do this. So pushing 56 is not too difficult. It's a little bit tedious, okay, because okay, so you should probably settle for one or the other, sequence. So you should probably just decrement and then you specify what to save on the stack. Now this part is definitely just a convention. It's up to you, because when you look at line 5 and line 6, the ordering between those two lines is not important. They do not depend on each other. Okay, you can either decrement the stack pointer first, or you can put something into the register, that you'll be storing later. So the order of line 5 and line 6 is not important, but you should probably settle on a particular pattern, just so that you know what the order really should look like in your own code. So I'm going to use this, kind of order, which is allocate first, and then we decide what to do after the allocation. Pushing 17, kind of the same deal, okay? You reserve the space, make one of the registers, A, B, or C in this case, the constant that we want to push on the stack, and then store that onto the stack, okay? Then we have the usual call, right? The usual call is decrement D to save the space for the return address. LDI A, now that we know that little trick, we can use that trick, .5 plus. Now this is where it is important to know which one comes first. If I switch the order between line 13 and 14, the LDI would need 1 extra byte. It would become .6 plus instead of .5 plus, because we would have the additional instruction of decrement D between the LDI instruction and the point where it needs to go back to. Okay, so that's why I said, make your use a consistent ordering, okay, so that you don't forget, and accidentally use the wrong order when it does matter. Okay, so now we can do the usual stuff. Store that again to where the stack pointer points to, JMPI to the subroutine, which is called Diff, and we have to clean up the arguments, because even though the subroutine itself is going to clean up after the return address, we would still have 2 additional items on the stack, which is, respectively 17 and 56, because the caller put those things on the stack. So once again, it is the convention, of the caller, cleaning up after the arguments. So cleaning up these arguments is actually pretty easy. All you have to do is to say increment D twice. That's it.
You didn't get rid of them, you just made it so they're invisible, and you will overwrite them next time.
But you have to keep track of which locations are available again. So incrementing D twice is necessary if your program still have something else to do. Now, since the next instruction is halt, so technically speaking, without line 18 and line 19, the program is not going to crash, but the stack would not be balanced. In other words, when the program starts, the stack started off with the stack pointer was pointing to 0. We want the program to go back, or we want the stack pointer to point back to the same location when it started. So that's why your line 18 and 19 are significant, because we want the stack pointer to be balanced. Okay. So this is not about whether the program is going to do the work correctly. It is about whether we demonstrate that whatever we allocate, we also know how to deallocate. Yes?
So there's no variable or anything that we could increment or decrement more than once. We just have to call once each time. Say if I want to do it 3 times, I have to actually put it down 3 times. There's nothing else I could do, like where it would be like increment D like 5, or there's no implementation like that.
Well, if you look up the opcode table, none of the opcode can support that. But if you look up the architecture, it cannot be supported. There's just no way to add a constant to a register, because there's no path going from memory directly to one of the inputs of the ALU. So I'm telling you how to answer those questions. So in the future, when you have questions like that, you can look up the opcode table, but the opcode table only tells you what we have implemented using microcode. So it is possible there's one thing that the architecture does support, but we don't have the microcode to do it, with an opcode. But when you look at the architecture itself, that is the hard limit. It's like, okay, we don't have a path going from the data port of RAM to one of the inputs directly into one of the input of the ALU. So there's no way we can add a constant to a register, unless we change the pathways of the architecture. Then we might be able to do it. Is that okay?
Yeah, no,
Okay, cool. All right. All right, so this is main, okay? So now we're moving on to diff. We know how diff is going to end, okay? Because diff needs to return a value in register A. So that means, when we retrieve the return address, we have to put it into register B. There's no other register we can put it into. Well, okay, I shouldn't say that. We have register B or C to choose from. I'm just choosing register B in this case. Increment D so that we deallocate the return address. That's the responsibility of the subroutine being called. And then we have a JMPB instruction. That's the last 3 instructions for diff. We know that already. So now we can go back and say, now what do we do? What do we do to access parameter X and parameter Y that are also on the stack? So to answer that question, it is really helpful to understand, how the stack, what the stack looks like at this point. What is on the stack right now? Okay, so if you look at register D, what do you think is register? What is register D pointing at the entry point of a subroutine called diff, like this? The return address. Very good. Okay, so the stack pointer D is pointing to the return address. Now, what is the return address? I don't know. Okay, from the subroutine's perspective, it doesn't know who is calling it. So all I can say is register D points to the return address. What is the one thing that we push right before we push the return address? Which parameter is that? The first parameter, okay, which to the subroutine is known as parameter X, right? Okay, so we know that D plus 1 is pointing to parameter X. And the first thing we push on the stack, which has the highest location, is going to be what? Parameter Y. Okay. So this is important. Okay, you can draw a picture on a piece of paper. You can use this notation. You can use a spreadsheet. But whatever you do, okay, have a mental picture of what things look like on the stack. Okay. So knowing this is the picture, now we need to say, we need to retrieve X, we need to retrieve Y, put those things into registers, and then do a subtraction. That's what we need to do. So what are we going to do? Okay. So I know very little about human psychology, but I think most people are thinking, I think this is what I want to do. And this is what I want to do next. Then all I need is a subtract AB, and we're done. But it won't work, right? It won't work because the assembler is going to tell you, it's going to vomit on you, okay? Then you go like, well, why would the assembler vomit on me? It's because there's no way to support this type of addressing mode. Look up LD. What does LD want? LD wants 2 registers. One register for the register being changed, and the other register to serve as an address. D is okay. D itself is a register. We can definitely dereference using register D, but you cannot just say add 1 to whatever D has and then dereference that. That doesn't work. Okay. We have to use register C. So don't change register D itself, okay? And I will explain why that is not a good idea later. So the first thing you can do is copy register. There are many ways to do it, okay? I'll show you both ways. One to work with one to do X and one to do Y, okay? So you can do something like this, okay? CPR CD. So now C equals to D, right? And then you can say increment C, whoops, so that C becomes the address of X. Then you can say dereference C, so that A becomes the value of X. Okay, so that's one way to do it. The other way to do it is, I wouldn't say trickier, but it's another way to do something is to LDIC with 2, okay, and then you add CD. So now C would be the address of Y, and then you can do the same thing. Yeah, it's okay. Give it a moment. It'll fix itself. I think it has to do with my little dongle here overheating. Yeah, because it does feel kind of warm. So I'm going to use a Dremel to improve its cooling. Maybe a Dremel and a small, 5-volt, fan, and some, not epoxy. I found a much better glue than epoxy. They're called a UV cured epoxy. Those things are great. Yeah, I have a little UV torch or flashlight. So you just so you have to drop in a relatively dark environment because you don't want to clog up the nozzle. So you put a drop and then you use a UV light shine on it, and it's like in 20 seconds it's all done. Yep, but it smells. It smells really bad.
Get the clothespin.
Huh?
Get the clothespin to put on your nose.
Get a what?
So get a clothespin to put on your nose.
Oh, or stop breathing. All right. So I have just shown you 2 ways to do it. Now, if you keep track of where register C is, you can just say instead of doing this, you can just increment C, because it's the next location that you want. Okay, so there are many ways to do it. The whole idea is you have to access X and Y relative to what register D is pointing to, but don't change register D. Okay. All right, so that's the whole subroutine, and yeah.
So, wait, never mind. Sorry.
Okay. Let me see how much time. Yep, we got plenty of time. Go ahead.
Do you ever store the result of the subtraction?
Yeah, it's automatically stored back into A, because when we have subtract AB, the result is stored into A. So
Subtract command?
yes, because subtract always stores. So this means A gets A minus B, which is the same thing as X minus Y now. Yep. All right. So I think I claim that this program gets what needs to be done. So now we can go ahead and just run the program and see whether it gets the job done. So Control C, and then switch back to the assembler. Okay. Okay, delete. Go back to the first cell. Paste. Change to RAM file. Now all of this stuff here, that I'm doing manually probably can be done using Google Script, or to a large extent can be done with Google Script, and a little bit of client-side, scripting. So for those of you who want to kind of take on a good challenge, you can give it a try. I think that would be a great project for the hackathon on December 7th. Automate tax assembler, so that you can have the entire chain done automatically. This is the file containing the source, and I just want the trace analyzer display on the browser when everything is done. It can be done. It's just a whole lot of various kinds of scripting. All right, so we got the file saved. Now we go back to the command line and we run this, and this time we use div.csv. Okay, it's all done. And then we go back to the assembler, trace analyzer. And we do a file, import, upload. And this one is the same as log.tsv. Replace current sheet, tab, and no. There we go. We go to analysis and start from the beginning. Okay, no instruction, nothing too exciting happening. Register D got initialized to 0. Decrement the stack pointer right over here. And then we store 38 in hexadecimal. You saw it just changed, right? That's because the spreadsheet was trying to catch up with all the calculations, so it just got changed to 38. So 38 in hexadecimal is 3 times 16 plus 8. 3 times 16 is 48. 48 plus 8 is 56. So we're pushing 56 right now. So now the next instruction is the ST instruction, and that's why we see 38 being stored at location FF. So that's why we are done pushing 56 at this point. Okay, this is 56 getting pushed. We decrement the stack pointer again to get ready to push the next byte, which is 11 in hexadecimal, which is 16 plus 1, which is 17. And that is pushed at this point. So we have now FF storing 56 and FE storing the 17. Okay. And then we push something else. Okay, you can see the stack pointer is now decremented again to make space for the return address. The return address is, let's see. Oh, it's one. No, it's not 11. It's decremented. Where did I read that? It's 11 again. That's why it didn't show up. I could tell it's 11, because the LDI instruction is reading location 0D to get the constant that it needs to update register D, and it turns out to be 11. So in this case, it just so happened that the return address and the first argument are exactly the same. They're both 11. Okay, what are the chances? Okay, so that's why we have 11 stored at location FD. So when you look at the stack at this point, we have in decimal, 56, 17, and then in hexadecimal 11. This is X, this is Y, this is the return address. This is what is happening on the stack. Now I'm putting this on the whiteboard because I have presented this already in the text of the program. It's just that I want to kind of give you a visual idea of what is happening on the stack. So after this, we have the unconditional branch to diff, okay? And the unconditional branch to diff is the JMPI instruction. It is at location 0F, and 14 is the entry point of diff, okay? So when you are doing this, okay, you might want to open up the assembler, particularly the assemble tab on a different window side by side, because this is really helpful. Because looking at the assemble view, you can tell what we are pushing on the stack, and on row 14 you can also see right here that the return address turns out to be 11 in hexadecimal as well. So that's why we have two pushing of 11, but the first one is for parameter X, and the second one is for the return address, which turns out to be the same value. Okay. In the assembler window, you can also tell where is the what is the address of the subroutine, because the subroutine is diff, and you can see it is at location 20. This is not in hexadecimal. This is an actual decimal number, which is 14 in hexadecimal. So between the assemble tab of the assembler and also the trace analyzer, one will show you what the program looks like, in a static way. The other one shows you what happens when the program runs. So when you combine those two, you should have a really good idea of what is going on with the program. Okay, so getting on to this. Okay, so at location 14, the first thing we needed to do was to retrieve X. Okay, so we first copy register D to register C, and that's why register C is also FD at this point. And then we add 1. Okay, we add 1 to register C, so it, instead of pointing to the return address, it is now pointing to parameter X. And then we retrieve parameter X and put it into register B. Okay. And then we increment, we use the other approach of loading a 2 into register C, and then we add register D to register C. So register C is now at location FF because 2 plus FD is FF. And because it's an addition, we can also see the flags actually getting changed in this case. And then we retrieve whatever is at that location. It is 38 in hexadecimal. We put that into register B. The first one we put into register A. So now we have the subtraction. The subtraction results in D9 as a result. Okay. So we want to double check, does it make sense that when you have 1, 1 in hexadecimal minus 38 in hexadecimal, should we end up with D9 and a borrow? Okay, so let's do that part in Notepad. All right, so we have hexadecimal 1, 1 minus hexadecimal 38, and we'll do it in the long format, which means we keep the partial sum, partial difference in one row, and then we have the borrow in the separate row. So this is always 0. 1 minus 8 in hexadecimal, what should it be? Well, we need a borrow. So when you have a borrow, the 1 becomes a 1, 1 in hexadecimal, which represents the value of 17. 17 minus 8 is 9, and 9 is just 9 in hexadecimal. Okay. So we have a 9 here, but it does end up with a borrow, so the borrow goes here. Are we doing okay? Okay, then we have 1 minus 3. 1 is less than 3, we have a borrow. So it becomes 1, 1. 1, 1 in hexadecimal is 17. 17 minus 3 is 14. 14 is E in hexadecimal. So we have an E here. And then we have an overall borrow, which is reflected as the carry bit in the flags. So now we have the second subtraction part. So 9 minus 0 is just 9, and E minus 1 is D. So the end result should be D9 with a borrow. So let's go back to the trace analyzer and see if that is what we got. Yep. So you can carry out subtraction in hexadecimal. It's just a little bit awkward sometimes, because you have to remember when you borrow, you're borrowing 16 from the next available column. You're not borrowing 10 from the next one. But once you understand that concept, you can actually carry out hexadecimal subtraction without having to convert into base 10 first. All right, so everything is good. And now we're ready to return. So this time we are loading the return address into register B, getting ready for the return operation. We increment the stack pointer because the subroutine being called is responsible to deallocate the return address. And then we perform the unconditional branch of JMPB. That's what is at location 1E. And then that goes all the way back to 1, 1, which is in main. In main, we have 2 increment instruction. So the first one increments the stack pointer from FE to FF. The second one will increment the stack pointer, which is register D, from FF to 0, 0. And then at location 1, 3, that should be the halt instruction. And that's the end of the entire program. Yep.
Why don't the flags change?
Huh?
Why doesn't that flag change?
The flag change where?
From,
Because increment does not change the flag. Yep. Neither increment nor decrement would change the flags, and I specifically derived the logic so they do not change the flags. Yep.
So that is the only way to deallocate the stack, or the memory on the stack.
You can do an add too. You can say LD, you can say LDI, whatever register, let's say A with 2, and then just add A to D in this case.
Oh, that's what I was asking earlier.
Yeah. So you can do it that way too.
Okay.
Yeah. So if you have a lot to deallocate, like if you have 20 bytes to deallocate, instead of using 20 increments, LDI A20 and then have add DA, that's a lot more efficient. But we only get 1 or 2 bytes, so it's actually faster to use the increment. If you have 3 bytes, it's kind of a toss-up. But anything after 3 is, the LDI plus an add instruction is more efficient.
All right, that makes a lot more sense.
Well, there are usually several ways to do this thing. Yeah.
And those values are still there until they're overwritten in the stack, right?
That is correct because we don't have interrupts. Okay, but once you have interrupts, getting into the whole thing, everything below where the stack pointer points to can be modified without you knowing it. So that's why we'll talk about this the concept of a stack. I mean an interrupt. Well, today we have 4 minutes, so we can start with that concept because I think it's important to understand why we should not increment the stack pointer until you're absolutely sure what it's pointing to is of no use to you anymore. Okay, so we can get started with the concept, but we won't be able to finish the concept today. There are two ways to handle input-output devices. One is called polling, which means you ask the I/O device, do you have something for me to process? And you keep asking the question in the loop. The second way is called interrupt, which means whatever device that needs your attention, that needs the attention of the processor, will raise an interrupt. Okay, electrically, it really is just pulling one of the lines low, okay, to let the processor know I need your attention. So that's technically what's happening. But in terms of the concept, it's easy to explain. Okay, so let's say I am the processor. Okay, Tack is in his office hour. I'm the processor. Okay, I can do a lot of processing. And you guys would be the I/O device. Okay, you're coming to my office and you want to ask me a question. Okay, so when I'm in my office, do you think I keep looking over the cubicle wall and see if somebody is waiting or have a question for me? No, I'll be on League of Legends. I'll be reading Quora. I'll be doing all kinds of stuff that is of interest to me, right? So what happens when you have a question? Go like, okay, I have to go see Tack. Well, you come into my office, you knock on the cubicle wall, and go like, hey, Professor Tack, I got a question. That is raising an interrupt. Okay, you're trying to get my attention. Okay. So the idea is, what does that have anything to do with the stack, right? Well, I don't want to lose track of what I'm reading on Quora. I don't want to, well, with a game, like, League of Legends, I can't do anything about it. But with a game that I can actually pause, I would pause the game, right? I would press the key and say, okay, I'll pause the game, and then I'll answer your question. Then after I answer your question, I will unpause the game to resume what I was doing, right? That is pushing a return address on the stack, okay? Me trying to remember what I was doing before you ask me a question is pushing a return address on the stack so that when I'm done answering your question, I now know where to get back to. Is that making any sense? That's why when you have the mechanism of interrupts, that particular mechanism also makes use of the very same stack that we are currently using to push the return address, the parameters, and all kinds of stuff. Is that okay? So now the question is, can you anticipate when an interrupt is going to happen? What is the nature of a particular interrupt? What can cause an interrupt in an actual, computer? Okay? Don't look at that as a computer. That is an inferior computer. This is a superior computer with tons of I/O devices, right? So whenever you touch the screen, okay, it's an interrupt. Whenever you shake it, okay, the accelerometer says, okay, I need to display something on the screen. That's an interrupt, okay? Whenever you say, hello, Google, okay, it doesn't work. Maybe it's working on yours, right? You guys have your phone, you're buzzing now. Okay, Google. Okay, Google. There we go. Okay, those are all interrupts, okay? Those are all interrupts. Interrupts are what we call asynchronous when it comes to the execution of your program. In other words, you can never anticipate when interrupt is going to happen. Okay? So it can only happen between the execution of two opcodes, cannot be during the execution of one opcode, but it can be between the execution of any two opcodes of your program. And you have no idea when it's going to happen. So that means the moment you increment D, interrupt can happen and make use of the same location that you have just deallocated. And there's no way your code can ever tell that an interrupt just happened. So that's why you don't want to increment the stack pointer unless you're absolutely sure that you, in your own program, you don't need that location anymore. Because interrupts all happen in the background and they're asynchronous and you have no idea when it's going to happen. So there, just use the 4 minutes to explain the reason why you do not want to increment the stack pointer in your own program unless you know that you don't need that location when interrupts are in place. The toy processor does not yet have the ability to handle interrupts, but in terms of concept, we want to be careful and use the same approach as all the main other processors out there. Okay, so when we get to the lab, we'll have a kind of new lab to do. I don't think it's going to take up too much time, so we'll deal with that later.